Ordinary least squares, simple and multiple linear regression analysis.
This is the fourth geostatistic course about kriging and cokriging interpolation and mapping. Remember that you have already available the first lesson that it was about ordinary kriging, also the second lesson that it was about universal kriging, and now we are working on the third lesson that is about regression kriging. You can watch the introduction, also the first part that is about how to create a grid using a shapefile with R and QGIS, and today you are going to see the second part. This second part is related with ordinary least squares. The goal of this lesson is to complete a full analysis of the first order trend surface and also the second order trend surface. We are going to do that analysis with the software R. Then at the end we are going to export the raster file to QGIS. Remember that at the first and second lesson about ordinary kriging and universal kriging, we did a full integration of R in QGIS. But in this third lesson, most of the time we are going to be using the software R because of the flexibility of this software in terms of completing the regression analysis. As we said at the previous lessons, the regression kriging assumes this model, where the variable of interest located in a specific coordinates of the space is equal to a deterministic model plus an stochastic model. The stochastic model can be solved using the ordinary kriging, but the deterministic model can be solved using different types of deterministic models according to the data set. And today we are going to be working just with ordinary least squares. If you want to have full access to all the content of the course, just go to the GeoRGV community website at gscourse.online. Then go to courses, select the fourth geostatistic course interpolation and mapping of kriging cokriging, then get enrolled, and then you are going to have available the option to start learning. Then press start learning, and here you have the introduction for the fourth geostatistic course. Then you have the first lesson that is about ordinary kriging, in total 2 hours 30 minutes of content. Then you have the second lesson that is about universal kriging. In this case you have 4 hours 30 minutes of content, and now we are working on the third lesson. On the third lesson you have the introduction of the lesson, then you have the first part that is about the interpolation grid. Then you have also the second part, that is the part that we are going to talk today, that is about ordinary least squares. Also here at the lessons, at the bottom, you have exercise files where you can download all the scripts that we are using in this lesson and also the spreadsheet. You can also follow the lessons through the GeoRGV community channel in YouTube. As you can see here, we have all the lessons, but in YouTube there are some restrictions. But if you want to watch it, you also can follow the course. Then we are going to open our studio and we are going to create a new project. Then go here, File, New Project, New Directory also. New project. Name of the project is going to be ordinary least squares, and we are going to save in a different folder that is going to be here. I'm going to create a new folder that is going to be ordinary least squares, and I'm going to save inside of this one. Okay, and create a new project. Now what I'm going to do is open the windows for the scripts. And I'm going to paste what I did already. Paste. And we gotta start to run the scripts. First, ordinary least squares. Then we want to add the directory and load the data. First, we are going to check if the directory is good. Then we have this directory. Then if we want to change the directory, we can use this script over here. But as this directory is good for me, I'm going to copy this one. I'm going to paste just to use the script, right? But we don't need to use it if the directory is good. But just to show you how you can change the directory. Then run this script. Then we can check again. And that's the directory that we want here at the bottom, okay? Then the next step is to load the data set. Then we have to verify that this link is the good one. I don't think so. Then I'm going to look for my data set. My data set is in this folder. Then what I want is this link. Then I'm going to copy this one. I'm going to paste over here. But I have to change the direction of the dash bar. For this direction, this one, this one, this one, this one, this one, this one. And what I want is to remove all these ones from here to here, because that one is the example I used. Then I'm going to remove this one, but I'm going to leave this one because that's the name of the file, okay? Sorry, I'm going to remove this one, and the name of the file is this one. And I want to leave the same name, okay? Then I'm going to run this script here. And now my data set is over here. As you can see, 85 observations of 4 variables. You can open this one also. And the next step is to create a backup of the data set. The data set, I put the name A because for me it's easy to manage. You can put any name, and the backup is going to be A2, okay? Then we can run this one. Now we have the data set for A and also the backup. And now we can check the data set. First, we can see the structure. And here we have the information, and it's saying that this object, it's a data frame with 85 observation of 4 variables. Here we have the name of the variables, ID, X, Y, and groundwater, and the value of these parameters. Then we can see a table with this script, view A. And that's the table with the 4 variables. Remember that X and Y are UTM coordinates, and GW is the groundwater elevation, okay? But this one could be any other parameter. In this case, it's the groundwater elevation inside of a piezometer, but could be the concentration of zinc, could be the pH of the soil, could be the electroconductivity of the sample took in this location. It could be any other parameter. Then the next step is the head. A is to see the beginning of the table. As you can see, that's the first value, the 6 first values of the table, and the tail is to see the last 6 values. Is this one for the last 6. And now what we are going to use is another library. This one is ggplot, and with ggplot we can make a different type of graphics. It's pretty flexible and we can make a very nice graphs. I already saved my project, as you can see in this screen over here. Just to do that one, go File, Save As, select a folder, select a name, and then save. Okay, now I'm going to run the ggplot. Then I'm going to see what is the relation between the variable groundwater and the variable X. I'm going to do a basic scatter plot, and I'm going to use the ggplot. Then with this script, I'm putting here the data set. I'm putting here what we want to see at the X axis, and also what we want to see at the Y axis. And also for the the plot, I want a geometry that is going to be points and with this size. Remember that all the variables here are in meters, the UTM are in meters, and the groundwater elevation is also in meters. Then in this scatter plot, at the x-axis, we are going to have the x-coordinate, and the y-axis, we are going to have the groundwater elevation. Then we can run this script, and then we are going to have here the graph. Here we have the groundwater elevation in meters, and here we have the x-coordinates in meters. Then, as you can see, as we are increasing the x-coordinate, the groundwater elevation has a lower number. It means that the groundwater elevation is deeper, okay? Because the groundwater elevation here is measured from the sea level. Then as we are moving in this direction at the x-coordinate, the groundwater elevation is deeper. Then we can consider that there is a trend, right? And the trend is this direction. Then with the next script, what we are going to add is a regression line for this data set. Then the script we are going to use is this one over here. Then we can run. And this script is the same as before, but we added this line over here to indicate that we want to see a first order polynomial fitted in our data, and is this blue line. This blue line is fit on the data according to the ordinary least squares, and we are going to talk about the ordinary least squares now. As you can see, when we are using this script over here, the software is telling us that the geometry smooth that we are using is this formula, where where y, it's the dependent variable of x, that is the independent variable. It means that the value of the groundwater depends on the x-coordinate. That's the first order polynomial, and is this blue line. Then I take this image over here and I put here in a graphic to see better. Then for the simple linear regression model, what we have is this equation over here, where we have the dependent variable that is equal to the coefficient. This coefficient is the beta sub 0, and that one is known as the intercept, plus the independent variable, that in this case is x, multiplied by the coefficient b1, that is the slope coefficient, plus a random error term. Okay, then the linear model can be expressed with these two components, the linear component and the random error. The linear component is the deterministic model, and the random error is the stochastic model. As we saw previously in this image, is the same as this one over here, right? This one is the deterministic and this one is the stochastic. Here what we have, the deterministic is all this one over here, and the stochastic is this part. Why this model is a simple one? Because we have just one variable to explain this variable. As we are using just one variable, this is a simple linear model. When we are using more than one variable, that one is going to be a multiple linear model. Then in our case, we try to explain the groundwater elevation according to the x-coordinate in this case. Then we have this coefficient, that is the intersect, that is the value when this line cut the value of 0. When we have 0 at the x-coordinate, then we make the vertical, and the point this line cut is going to be the beta sub 0, and the slope is the slope of this line over here. This line has a slope and is going to be the coefficient beta sub 1. As we add in more explicative variables, independent variables, the model is going to be more complex. And each independent variable or explicative variable is going to have their own coefficient. Then the next question is why this line is the best line? Why could be any other different line? And to explain that one, we are going to use the next slide, that is this slide over here. Then as you can see, here we have a data set, that is the reg docs, and we have different lines. From all these different lines, what is the best? The best line is the line that minimizes the distance from the observation points to the model, okay? Then we are making the summation of all this distance, we square this distance, and then we are going to have a value. Then the line that makes this value minimum is going to be the best model according to the ordinary least squares. And how we can express that one mathematically using this equation over here. This one is the observation point, and this one is the predicted point. What is the predicted point? The predicted point is the projection of the observation point on the model, is this yellow point over here. Then in our case is this one. Then here we have the observation point, that is the groundwater elevation in this point, in this coordinate. Then if we project this point on the model, we are going to have the yellow point. This yellow point is the predicted value. Then the model, the blue line, in this case, is the line that makes minimum this distance from all the data sets to the model, according to this mathematical expression. Then we have the observed value less the predicted value. We square this value and we make the summation of all the distance, right? And then we have the minimum value. That minimum value is the best fit for the data set according to the ordinary least squares. Now the next question is how we can pass from the observed values, these red dots, to the residual values. In order to do that one, what we have to make is this line to be 0. Then when this line is 0, what we are going to have is a graph like this one. And now what we have here is the residual values are no longer the observed values. Now are the residuals, because we make all these values here to be 0. When these values are 0, are projected this line over here, and what we have is this one. Then what we have here is the residual values. And now we can calculate other parameters like the residual standard error using the residual sum of squares here and the number of samples. Also we can calculate the total sum of squares. In this case, this one is the observed values and this one is the mean of the observed values. And also we can calculate the R squared with this formula over here. Now we are going to see how R is going to provide all these values. Then we can go to R and run the next script. Then we are going to define what is going to be our regression model. It's going to be as simple, because we are using just the X coordinate to explain the groundwater elevation. Then we are going to call this model as a model 1, and the parameters of the X and groundwater are located in this data set. Then we can run this one to save the model. Now we have the model here. And now we can see the statistics associated with that model. Then we are going to use the script summary model 1. And we are going to have here several information. First of all, we have the equation that we are using is this one. Then we have the residual, the minimum value, the first quantile, the median, the third quantile, and the maximum value for the residuals, okay? And then we have the coefficients. This one is the intersect. Remember that the intersect is the first coefficient, this one. Then we have the coefficient for the x. This coefficient is going to be this coefficient over here, b1, beta sub 1. And then we have the residual standard error. This residual standard error is the one we saw here. Residual standard error over here. And we have the r squared is this value over here. And is this equation over here. Also, we can see that the x variable, that is the x coordinate, is significative in the model because it has these 3 asterisks. Then in this case, the x coordinate is explaining 57% of the total variability of the model. 100% is going to be here number 1, but with the x coordinate, we can explain 57% of the total variability of the model. It means there has to be another variables that we didn't add it at the model that can explain more of the variability, right? For example, it could be the y coordinate, it could be the elevation of the terrain, it could be the precipitation, it could be the number of variables is infinite, right? And if we have all the variables, that is going to be an ideal model. We can explain 100% of the variability of the model, but that one never is going to happen. But with this variable, that is the x coordinate, we can explain the 57% of the variability of the model. That is really good, right? It's pretty high. But we can see that there is another 43% that we cannot explain. We don't know that variability comes from, right? And also we can see that information with the ANOVA table, and it's going to be the next script. Okay, in order to be the x variable, in this case the x coordinate significative, the value has to be less than 0.05, okay, this one. Also here with the p-value, as this one is smaller than 0.05, we can conclude that this model is also significative. It indicates that the model is also good. Now we can see the ANOVA table. And here we are going to see another statistics, okay? Here we can see the summation of the squares for the x variable, and also the summation of squares for the residuals. Then if we plus this one, what we are going to have is the total summation of squares, right? We was talking about here, total summation of squares is this equation over here. Then I created an spreadsheet with that information. Here we are working with the simple regression model, and we have this equation over here. With the groundwater elevation is depending on this model, that we have a lineal component over here, that is the deterministic part of the model, and we have the stochastic model, right? But now we are talking about the deterministic part. Then we have the summation of squares by the x coordinate is this amount. Then we have the summation of squares by the residuals is this amount. Then the total summation of squares is this value over here. That is the summation of this one and this one. Then what this amount, what variability represents. Then we can calculate that one with this equation over here, right? And also, because we know already that this value over here represents the 100% of the variability, right? Is the variability explained by the x coordinate plus the variability explained by the residuals that we don't know anything, right? We don't know is when we go to the graph. Sorry, no, I don't want to pick this one. If we go, no, yeah, here, we know just the variability by the model, but we don't know the variability by the residual. This value here is the residual, and we don't know how we can this variability can explain, because we don't have the coefficient to explain all this variability, right? Then the variability that we know for sure is just the variability explained by the x coordinate, and is this amount, and this amount can be calculated according to this equation over here. And what is the variability that we don't know anything? Is the variability explained by the residuals, and in this case is this amount, and here we have the equation, right? Then the residual summation of squares is this parameter, and is this value over here. Then the total summation of the squares is this value over here. That is the amount explained by the x coordinate by the amount explained by the residuals. And then what is the r squared? Is this value. We can use this formula to calculate that one. And that's the value that we get. And this value is the same as we can see over here. I mean this value over here. The multiple r squared. This value is the same as we calculated over here. Also, the values associated with the summation of squares by the x coordinate and by the residuals, we get that one at the ANOVA table. Here we have the total summation of squares for the residuals and the total summation of squares for the x coordinate. Then if we plus this one, what we have is the total, that is this one over here, and is also the same value as here. Now what I would like to see is the graph of the residuals. Then I'm going to add here one more script. Is this one. I want to plot the model one, but I want just this script is going to provide several graphs, but I want to see just the first graph. Then I'm going to run this script. And here I have the residuals at the y coordinate, and I have the fitted values at the x coordinate. And as you can see, this line now is 0. What is this line? This line is the same as this one over here. Here we have the observed values. Remember that the projection of the observed values on the model is going to be the predicted value. But when we make the trend line, the regression line, we make all these values over here 0. What we have is this graph over here. In this graph over here, what we have is the residual values. In this first example, we was working in 2 dimensions using the groundwater elevation and the x coordinate. But as you know, our case is a little bit more complex because we have x coordinate and y coordinate and the groundwater elevation. Then what we are going to do is work in 3 dimensions. Then I decided to start with just 2 dimensions because it's easy to understand. Because as we added more variables, more explicative variables, the model is going to be more complex and more difficult to understand, right? But if we understand the simple one, we are ready to go one step further and start with the multiple regression analysis model. And that's what we are going to do now. Then what we are going to do is create a multiple regression model that is going to be a surface of first order. Then that one is going to be the second model. At the second model, we are going to try to explain the groundwater elevation, but using 2 explicative variables or 2 independent variables. That in this case is going to be the x coordinate and the y coordinate. And all these parameters are located in this data set. Then we are going to run this script. And now the object is saved over here. And the next step is to see the statistics of this new model. Then let's go to make the summary of the model number 2. And here we have the statistics. Now, as you can see, here we have the formula, and here we have the values for the residuals. The minimum, the first quantile, the median, the third quantile, and the maximum value. And also we have the value for the coefficients. This one is the intercept. And then now we have one coefficient for the x variable and one coefficient for the y variable. And as you can see, both of them are significant because the value is smaller than 0.05. And also here we have that the multiple root square is bigger. It's indicating that with these two variables, we can explain more variability than the one we was explaining with just the x variable. Okay, because I can run also the summary for the first model. It was this one, and we can compare. Let me make this one bigger. Here is this one is the second model, okay? And this one is the first model. Then as you can see here, this value is smaller than this one. It is indicating that with the second model, we can explain more variability. And the model is still significant, okay? Then we can run the ANOVA. The ANOVA table for this second model is this one over here. Then here we have the summation of the squares for the x variable, the summation of the squares for the y variable, and the summation of squares for the residuals. Now I take all these values and I bring to the spreadsheet over here, and let's go to see a little bit. Here we have the equation for this model. And as you can see now, we have the two explicative variables, the x coordinate and the y coordinate, and then we have a new coefficient, okay? We saw this new coefficient over here at the summary of the model 2, is this new coefficient. Then when we go here, we can see that if the total variability is 100%, now we have the x can explain 57.8%, but now y can explain 31.1%, okay? And then we have the residuals that represents 10.9%, okay? But before, the residuals explain 42%, you know? The variability explained by the residuals is the variability that we don't know anything, right? But now we reduce that variability. That is indicating that the model associated with the first order trend surface can explain more variability, and the model is even better because now the variability explained by the residuals is smaller. Again, here we can calculate all these parameters according to these formulas. As you can see, the total summation is this one, and also we calculated the R square, but this R square is no good, 0.89. If you see here to R, 90 is the same as we get here, 8904. 8904, but when we are working with multiple regression analysis, we have to take this value. This one is not totally correct, then we have to use this one. Then the variability that can be explained by these two variables is a little bit smaller than this value over here, but it's still bigger compared with the one we was getting when we was using the simple model. In the simple model, as we are using just one variable, we can check this variable, this value, not this value over here. but the improvement is significant, right? Then the next step that we are going to see now is how we can make a representation of graphical representation of the model, right? Then I'm going to paste here what I did, then paste. I'm going to save this one, and then let's go to run this script. First of all, we are going to load this library. As you can see, it's not installed. Then we have to install the library. Let me put this one here. Then I'm going to install the package, but I'm going to cut the video because it is going to take time. Copy. Then when it is installed, I'm going to restart the video again. Then run the library again. Then I'm going to attach the data set just to avoid to add the data all the time as we was doing over here, right? Here at the top. If you attach, you don't have to be adding all the time. Then attach. Then we are going to create the grid for make the graphical representation of the model. Then we have to put what is the maximum X, the minimum X, the dimension of the grid, etc. Then at the next line, we are saying that we make the representation of this model. Then we are going to create some lines from the observation to the predicted. Then we are going to tell where are locating the variables. And with this script, we can create the model. And it is this model. Then if you change here the angles, you can see a different view. For example, 3, and here, I don't know, 30, for example. And then we can run again. And then you have a different view, right? But before it was better. 2 and 1, run. Then here we have the X coordinate, the Y coordinate, and the groundwater elevation. And we have the trend surface, that is this plane. Then the dots are the observations. I don't know why we don't have the line from the observation to the plane, but I can show you the work we did the other day with the universal kriging, because we was working with QGIS and we created the same graph. And here we have two different views of the same plane, right? And here we have the plane, and you can see perfectly the line from the observation to the plane. Okay, and this graph is the same but with different orientation. Then we have the observation points, and then we have the line that goes from the observation to the predicted value. The predicted value is on the plane. Then we have to understand that we have positive values when the points are above the plane, and negative values when the points are below the plane. These positive and negative values are related just with the residual values. When we make this plane to be 0, then below the line the residuals are going to be negative, and above the line the residuals are going to be positive. Now also we can visualize the residual values in a scatter plot that is going to be 2 dimensions. Then let me copy this one, copy and paste over here. But now we want the model number 2. It's going to be a little bit abstract and difficult to interpret, but the important thing here is that the line, this one, it's going to represent this model, right? This model, this plane over here. And then the values above the plane are the positive values, and the values below the plane are going to be the negative values. And here we have the residuals against the fitted values according to the first order trend surface. You can see here the equation. Now, the next step is to analyze the second order trend surface. Then I'm going to paste here what I did. And let's go to run from here. Then this second order trend surface, the equation or the formula is this one, okay? Now here we are going to consider the x coordinate, the y coordinate, the x coordinate square and the y coordinate square and the cross of y and x. Then run. That one is going to be the third model. Now we can see the statistics. First, let's go to see the summary. Then, as you can see, now we have 1, 2, 3, 4, 5 independent variables. This one is the formula. Here is the value for the residuals. As you can see, most of the coefficients are significative, less this one are not significative. It means that we can remove this value from the model because it's not adding anything to the model. It's not explaining any variability on the model. Then it could be removed. Then we can use the same formula but without this variable. Okay. Then again, the value is very high and is higher than the first order trend surface, and the model again is significative. It means that this model is better than the first order trend surface. Let's go to see the ANOVA table. And here you can see again the ANOVA table is indicating that this value is significative, this value is significative for x and y. Then this value, as we saw also at the summary here, is not significative and is not adding any information to the model, right? Then this one is also significative, but it's not that much because the value is very, very close to 0.05. And also, again, this one is significative, okay? It's adding some variability to the model. And this one is the summation of a square for the residuals. Then if we go to the spreadsheet, I'm not going to explain everything again because it's going to be the same as the other ones. The important thing here is that this model explains more variability than this one. Remember that we are not using this value. The value we are using is this one here, okay? But before, for the first order trend surface, it was 0.8 something. Let me double check. I don't know where it is. This one is for the first model. This one is for the second model. And we have 0.88. The improvement is not that much, because from 0.88 to 0.90 is not that much, but there is a small improvement. Then here we have the variability explained by the x square is 0.1, but the y square is 0.4. That's a percentage. And the variability explained by x by y is 0.6. Is, you know, we added a lot of new independent variables, but the improvement of the model is not that much. You have to know that we have in total 85 measurements, but here we have already 1, 2, 3, 4, 5 independent variables. And you know, we have to find an equilibrium, right? If we don't have too many measurements, we cannot have a very complex model with a lot of explicative variables. That it doesn't make any sense, right? At the end, the question that we have to make is this new model explaining more variability than the other one? And the answer is yes. It's not that much, but it explains a little bit. And it is worth it to add these new independent variables compared with the total of number of observations we have. And that's the point, right? Then later we are going to see a little bit more things in order to know if it is worth it, right? In order to know what model we have to take. Because looks like from the second to the third model, the third model doesn't explain too much variability, right? Then it is worth it, you know? And that's the point. And we are going to answer this question later. Now let's go to see the graphical representation of the second order trend surface, okay? For the first order trend surface, what we have is a flat plane, as you can see. And now for the second order trend surface, what we are going to have is a plane with a curve, okay? Then let's go to run this line over here. And this one is going to be the same as before, but for the second order trend surface, I mean for the model number 3, okay? That's the model number 3 is for the second order trend surface, okay? Then I'm going to run all these lines. This one is the same as before. And now, as you can see, we have a curve, okay? We fit a surface that is a curve in the data set. Then we have here a plane that is flat, and here we have a plane that is a curve. Also, again, we can run this script. Let me check over here, this one, to see the representation of the residuals. Here, paste. That one is model 3. And we can run to see the residuals. Again, the important thing is the line at 0. Then we have some values that are below the plane and above the plane relative with the residuals. Here we have the residuals, and here we have the fitted values, and here we have the formula that we are using in this specific case. Now we have to decide what model we are going to take. Then to do that one, I have a bunch of scripts here. I'm going to paste. And what is the best model? Then first we can use the ANOVA. Let's go to run this one. And with this script, we compare the simple regression with the multiple regression. That is going to be the first order. Remember that the first model, it was this model where we were using just the X coordinate. Then we trying to explain the variability of the groundwater using the X coordinate. For model 2, we try to explain the variability of the groundwater using the coordinate X plus the coordinate Y. Then when we compare these two models, as the p-value is smaller than 0.05, this p-value over here, it is indicating that the second model is better than the first model. How this script works, how the comparison works. Then it takes the first model, is this one, and it provides us the total summation of squares for the residuals for this model. Then it takes the second model, that is this one, and it gives us the same, the total sum of squares for the residuals for this model, and then make a comparison between these two values. As the second model explains less variability for the residuals because the value is smaller, then we can consider that the second model is better, because as we have as the total sum of the squares for the residuals is smaller, the variability explained by the residuals is smaller, And as you know, the variability explained by the residuals is the variability that we don't know anything, right? And as this value is smaller than this one, we have a p-value that is smaller than 0.05. And our interpretation is that the second model is better. Now, what is going to happen if we compare the second model with the third model? Remember that the second model is the first order trend surface, and the third model is the second order trend surface. Then we can run, and again we have the ANOVA comparison. Here we have the second model that is called here model number 1, and here we have the model number 3 that here is called model number 2. It's a little bit confusing, right? And the variability explained by this model, by the residuals, is this amount. The variability explained by this model is this amount. As this amount is smaller than this one, we have a p-value that is smaller than 0.05, and it is indicating that the second model, that in this case is this model, is better than the first one. I didn't say previously, but also is taking in consideration the degrees of freedom. These degrees of freedom depends on the number of explicative variables that we have in the model. But anyway, here the p-value is smaller than 0.05. Then we can conclude that this model is better than this model. But there is one thing that I don't like about the ANOVA comparison, you know, for the models, that you have to be aware that as we increase the degree of the polynomial, better is going to be the fit on the data, right? Here we pass from first order, to second order polynomial for the surface. And of course, the fit is going to be better, right? It's like here, for example, if we have a line that is going to be the first order, then if we make a second order, that is going to be a curve, then the fit is going to be better. And then if we make a third order, where we are going to have two curves, the fit is going to be better. Then if we make a third order, the fit is going to be better. Then always we are going to have this value here. Let me show you. The adjust R square is going to be higher as we increase the degree of the polynomial. Then the comparison of the ANOVA looks like in this case it doesn't work really well, right? Let's go to make an example. Here, what happens if we add a surface of first order? Let's go to C. Then we add that one, and we are going to create a multiple regression model that the surface is going to be a third order. And here, sorry, I didn't run this one, number 4. Then let's go to run this one. And here we have the formula. As you can see, in this case, we have a lot of explicative variables. We have 1, 2, 3, 4, 5, 6, 7, 8, and 9. And 9 independent variables, okay? Then we can run the summary. And as you can see, for this model, the values looks a little bit crazy, right? Here what we have is the significative variables, this one and this one. The only ones looks like are no significative, but looks there is no good values. It doesn't make any sense, right? Because for me, it doesn't make any sense, these values over here. Maybe there are problems related with multicollinearity. And also the ANOVA table, if we see the ANOVA table is not bad, you know, it's giving the variable X is significative, it makes sense. The variable Y is significative, it makes sense. This variable is not significative. We saw previously that at the second order trend surface, this variable was not also significative, that makes sense. This is significative, makes sense. This one is significative, again, makes sense, because also it happens with the second order trend surface. But this one is not significative. This one also is not significative. This one is significative, as you can see, and this one is not significative, okay? Then in this model, the only one is significative is this one, right? But we add a lot of variables, okay? And then when we are doing the comparison again with the ANOVA table, you are going to see that for this model, we can explain this variability. And for this model, we can explain this variability. And again, the p-value is smaller than 0.05, indicating that it's significative and indicating that this second model is better than this model over here. But the point is, when we pass from the first order trend surface to the second order trend surface, we saw that the improvement was very, very, very small. Then it doesn't make any sense in this case that the third order trend surface is going to make an improvement with respect to the second order trend surface, right? However, when we see here this value, the R square, for the third order trend surface, this value is higher than the value that we get for the second order trend surface, that was 0.90, okay? Then, as a conclusion, what I want to say that the ANOVA comparison in this case doesn't provide good results, right? Sometimes you have to use the common sense, and here in this case, for the third order trend surface, there is something that doesn't work really well, right? And a good example of that one is the values for the summary, right? Here, over here, that makes this one significative, and this one significative, and the rest are not significative. Then, in order to decide what model we are going to take, we are going to use a different criterion. And in this case, we are going to use the Akike information criterion. Then here you have, when you run this script, you have the information related with this statistic. I'm not going to talk. You can make your own search on Google about this statistic. And what we are going to do is calculate two different numbers. The first one is going to be the AIC, and the second one is going to be the BIC. The difference is that the BIC is more sensitive to the number of independent variables that you add to the model. And as the number of variables is really big compared with the total number of observations, is going to be a penalization. Then this value is going to be a little bit more realistic. Then we are going to run the number, the AIC number, for the model 1. Also, we are going to do the same for the model 2, 3, and 4. These values, they are not saying anything, you know. In order to have some information, what we have to do is compare the values to make the difference. Then that's going to be the delta. Okay, and we are going to do the difference between the first model with the second model, okay? Then we can make that difference, and then we can see what is the value, and that one is the important value. And then with this value, we can go to this table, and if that difference is bigger than 10, it is saying that the improvement between the two models that we compare is so big. Then the second model is better. And if the value is between 0 and 2, it's indicating that the improvement of the model is almost nothing, okay? Then when as closer is the values to 0, less improvement are between the two models, okay? When the value is bigger than 10, we have a big improvement. When the value is close to 0, we have a very minimum improvement, okay? Then in this case, as the value is 112, it's indicating that the improvement between the model 2 and the model 1, between the model 1 and 2, the improvement with the model 2 is very significant, okay, because the value is very big. Then we can compare now the model 2 with the model 3. Remember that the model 2 is the first order trend surface, and the model 3 is the second order trend surface. Then we can make the difference, and now we can see the value. And in this case, as you can see, the value is not really big, but it's still bigger than 10, okay? Then it's indicating that we have a big improvement from model 2, from the model 2 to the model 3, okay? Then we are going to take the model 3 because the improvement is so big. Then, big according to the number, okay? According to the number and according to this table. Then now we are going to calculate for model 3 and model 4. Model 3 is the second order trend surface, and model 4 is the third order trend surface. Then we can run this script, and again we can run this one. And as you can see, now the value changed quite, right? And now we are in this range over here, okay? That is closer to 0. Then in this case, from model 3 to model 4, the improvement is not that much, okay? But for me, the most interesting is this value, the VIC, because in this case, it's taking in consideration the observation and the number of independent variables that we are using in the model, okay? And if the number of variables is too big compared with the number of observations, it's going to be a penalization, okay? Because we are making a complex model for a number of observations that is small, okay? And then we are going to do now the same. For the model 1, we are going to get the number, for the model 2, for the model 3, and for the model 4. And now we are going to compare the model 1 with the model 2. And for the model 1 and model 2, the value is 110. It's indicating that there is a big improvement from model 2, from model 1 to model 2. Then we are going to take the model 2. Then let's go to see what happened with model 2 and model 3. And again, we have improvement. It's not that big, but we are now in this range that is indicating that there is an improvement. And now let's go to see what is going to happen with model 3 and model 4, okay? Remember, model 4 is the third order trend surface, model 3 is the second order trend surface. And as you can see now, the value is negative. It's indicating that there is no improvement at all. Even the fourth model is worse than the third model. And the reason is because here we added a lot of independent variables according to the total number of observations we have. We have 85 observations, but we created a model with 9 independent variables. And here we have the penalization. It's indicating that there is no improvement. Then in this case, we are going to take the model 3. When we are using this one, we saw that the third model is better than the second model. And when we are using this one, what we saw is that the third model is better than the fourth model. Then the model that we have to take is the third model. And the third model is the second order trend surface. Now we know what model we are going to use. That is going to be the second order trend surface. But when we are working with linear regression models, we have to cover some assumptions. And to cover that assumptions is really important, because if we are not covering the assumptions, the values that we get for the coefficients are not good. Then if the values are not good, the model is not representative of the data. Then we have to make sure that we are covering all the assumptions in order to verify that the model is good. The first assumption that we want to cover is the linearity. The relationship between the dependent variable y and the independent variable or variables x or x sub n is linear in its parameters. It means that it is an additive model. Beta terms appear as independent or as a coefficient of the independent variables. And here we have some examples. Then, first of all, the model that we have to fit in our data has to be a model additive, okay? It means that we plus the terms. As you can see over here, we plus the coefficient plus the variable multiplied by the coefficient plus the error term, okay? It's additive because we plus all the terms in this model. The same happens in this model. This one is a simple regression model. This one is a multiple regression model. And this example is for a first order trend surface. One important thing also is that the beta terms appear independent, as you can see here, or as a coefficient of the independent variable. As you can see over here, is a coefficient of this variable. And again, the model is additive. This example is for a second order trend surface, and again is additive, is an additive model. And also we can see the beta terms, they are independent as the beta sub 0, and also a coefficient of the variable, in this case for beta sub 1, beta sub 2, beta sub 3, beta sub 4, and beta sub 5, okay? But as we can see in this example, this one it's not a linear model, because beta sub 2 it's not an independent coefficient, it is beta sub 0, and also it's not a coefficient of an independent variable. Then in this case, we have to consider that this one is not a linear model. The same happens here because beta sub 1 and beta sub 2, they are multiplying, and also happens here because it's not an additive model. But sometimes even this one is not an additive model, we can make a transformation and become this model a linear model, and this one is the example. Also, we can verify that our model is not covering the assumption of linearity with this graph, where we have the, let me make this one bigger, where we have the residual values against the fitted values. And what we want is something like that, right? When we have a shape like that one, is indicating the no linearity, okay? And if we go here and we run, for example, this one is for the second order trend surface. When we run this script, the plot for the residuals, we can see here that there is no any trend, right? This graph is close to this one over here, right? Doesn't look like something like that, or something like that, or something like that, that indicates that there is a trend on the residuals. And if it happens, it indicates that the model that we fit in our data is not the proper one, right? Maybe sometimes we try to fit a first order trend surface and we are still having a trend on the residuals. Then maybe it means that we have to fit a second order trend surface or a third order trend surface, right? But what we want to have is something like that in the graph of the residuals versus the fitted, okay? In this graph over here. Then after fitting the model, if you are still having a trend on the residuals, maybe you have to do a transformation of the data, right? And even if the transformation of the data doesn't work, maybe then you cannot use a linear model. Then you have to use a different model, okay? That's how you can fix the situation, right? Maybe you are trying to work with a linear model with ordinary least squares because it's easy to understand the math behind, it's very easy to make an interpretation, but maybe it's not the proper model for your data, right? And then you have to consider then to use a different type of model. You can use, for example, an additive generalized model. The next assumption is going to be the normal errors. Residuals are independent and normally distributed. Then how we can verify that assumption? Then we can verify graphically, because maybe we can do a histogram and see how looks our histogram. Also, we can do a cookie plots, and also we can do a box plot. But also we can quantify numerically the normality of our data doing some tests. For example, we can do the Shapiro-Wilk test, or also the Kolmogorov-Smirnov test, or also we can do the Anderson-Darling test. Then let's go to see these things on R. I'm going to paste here what I did already. Paste and save this one. And then let's assume that the model 3, that is the second order trend surface, is the best. And then we have to question, it is covering the first assumption, the linearity. We was watching already that is covering that assumption. That now it comes the second assumption. It is covering the second assumption, normal error. Then for do that one, we can do the histogram. Then first of all, I would like to get the residuals from the model 3. Then with this script, I extract the residuals, is these values over here. Then I'm going to do a simple histogram with the residual values. Is this histogram, but this histogram doesn't provide too much information because the number of bins is not the good one. And I would like to see also the mean value, the median, and I did with histogram with the ggplot that is more nice and have a lot of information. And is this one. Then here with the green line we have the median, and with blue line we have the mean value. The mean value has to be 0. It's indicating that we fit the correct model, okay? And as closer are the median to the mean value, better and more symmetric is going to be the histogram, right? And also it's indicating that the data is distributed normally. Here the shape of the histogram is really good, and for me it's the distribution of the data, it's quite normal, okay? But in order to verify that one, we can run a test. In this case, we are going to do the Anderson and Darling test, and this test is located at the library Nord test. If you don't have this library, you have to install. I'm not sure if I have this library installed in this computer. No, then I have to install the library. Then I'm going to paste over here and run this script. I'm going to put here a pan because I want to avoid to run this line again. And now I'm going to run the library. Now it's working, and I'm going to do the Anderson-Darling test. Is this one, as the p-value is higher than 0.05, we can say that the data is normally distributed. And also we can do the QQ plot with this script. And now what I want is the graphic number 2. is this one. And in this graph, what we want is to have all the dots on the line. Okay, this one at the tails is not really good, but as we did the test and it gave us a p-value that was bigger than 0.05, we can assume that the data is normally distributed. But the QQ plot is also not that bad. Then the next question is what happens if our residual values are not normally distributed. Then we can fix the situation doing the data transformation. We can do the transformation on the original data, then take the residuals and see what's going on. And if we still not having a normal distribution of the residuals, then we can use another different linear model that could be the generalized least squares. In this case, we don't have to cover the assumption of the normal distribution of the data. Now let's go to move on to the next assumption, that is going to be the constant error for the variance. Okay, what we don't want to have is heteroscedasticity in our data. We want to have homoscedasticity. How we can check that one? Graphically, we can do a plot of the residuals versus the fitted values, as you can see over here. And what we want is these values and these values be constant, like here, right? When we have here, for example, these values and this one is increasing like a fan, like is showing in this graph, then we have a heteroscedasticity, and then we cannot use the ordinary least squares. Then in our case, let's go to R, and that's not this one, not this one. This one is the residual values for the second order trend surface, and here looks like that the like we have homoscedasticity, but as we have this value here, maybe we can have some heteroscedasticity. Then what we want to do is to run a test that in this case is going to be the Breuchan-Pagan test that is going to quantify if we have heteroscedasticity. Okay, then we can go to R and run this line. This one is for the third assumption. Is it covering the third assumption? Constant error of the variance. Then we can run this one. We can run this plot, but we did already, is this one. And now we are going to do the test, but we have to load this library, LM test, but I don't have this library installed. Then what I'm going to do is install the package first. Copy, paste over here, and it's going to be this package. Copy and paste, and I'm going to remove the pound. Then first this one. Let's go to leave the source while install the package. It is already good. Then we can run the library, but first let me put here a pound because I don't want to run this line again. Then run the library. And now we can run the test for the model 3. The model 3, remember, that is this second order trend surface. Then run. And as the p-value, as you can see over here, as the p-value is smaller than 0.05, the residuals do not present constant variance. The third assumption, it's not covered, okay? With this value, it's assuming heteroscedasticity for the model, okay? We are not covering the third assumption. But one thing is very right, that this value is very close to 0.05, right? We are pretty close to the limit, right? Then even that we are not covering the third assumption, we are going to do anyway the trend surface with the linear model, and then I mean with the ordinary least squares, and then we can compare the model, the final result, with the generalized least square to see if there is too much differences between the two models, okay? But as I said, we are not covering the assumption of homoscedasticity. Okay, we are not covering this assumption. It is necessary to cover the third assumption, and our data is having heteroscedasticity. But again, it's pretty close to the limit, okay? And at the end, the 0.05 is an arbitrary value, okay? We can put here 0.04, right? But in general, we are using 0.05. Then again, what we can do if we are not covering the third assumption, then we can do data transformation as I mentioned previously, and also use a different model. For example, the generalized least square is not very restrictive model, can take residuals that are showing heteroscedasticity, okay? Then that's the thing. Now the fourth assumption is related with the independence of the residuals, okay? The residuals are independent and there is no autocorrelation. There is no spatial autocorrelation. Then how we can check that one? Again, graphically with the plot residuals versus the fitted values and with the bubble map as I show you here. As we saw the assumption for linearity, what we don't want to see is any trend on the residuals. If there is any trend, if there is a trend on the residuals, it is indicating that there is a correlation with the residuals, okay? And then we have to fit a different model. But as we are going to do that one as a first assumption, I'm assuming that we are not going to have any trend on the residuals. Then the second step that we want to check is the bubble map. Let me show you here. Then what we don't want to see here at the bubble map, let me make this one smaller. First, what we don't want to see here is a trend, right? Because for example, if we have in this case, that is for the residuals for the first order trend surface, but it's just an example, could be also for the second order trend surface, right? Then the blue circles are the residual positive and the red circles are the residuals negative, okay? Then what we don't want to see here, for example, is all blue in this area and all red in this area, because that one is going to indicate that there is a trend on the residuals, and that trend is the first order, right? Then, for example, if we have blue, red, and blue, what we are going to have is a trend on the residuals that is going to be a second order, right? Because it's going to make a kind of curve. Then if we have, for example, blue, and red, we are going to have a trend that is going to be a third order trend surface, okay? Then we don't want to have that kind of trend on the residuals. Also, what we don't want to see is clusters, right? For example, in all this area, all red. In all this area, all blue. In all this area, all red. In all this area, all blue, right? That is going to make clusters for negative and positive residuals. And that one is going to be also autocorrelation, a spatial autocorrelation of the residuals. Then if that happens, that we have a spatial autocorrelation of the residuals, we cannot use the ordinary least squares. Then we can use, for example, the generalized least squares, because in that case, we can add that spatial correlation to the model. And we are going to see how to do that one on the next lesson. Now we are going to see how we can create the bubble map. Then I'm going to paste here the coding. And that one is the fourth assumption. Is it covering the fourth? Here I have to change for fourth. Assumption, independence of the residuals. Then we can run this line. And now we can see the bubble map with this code over here. We can add the grid also, and we can make this one bigger. And in this case, for me, the distribution of the residuals is pretty random, right? Looks like there is no clusters of negative and positive values, right? As bigger is the circle, bigger is the value of the residual for positive in a blue color and for red in a negative values. But for me, that looks like there is no clusters, right? But if you think you have clusters, you can do the analysis with the generalized least squares to avoid any problem, right? But for me, in this case, we are going to compare later the result that we get with the ordinary least square with the result that we are going to get on the generalized least square to see what are the differences, right? But at the end, if you can use ordinary least squares, that's better, right? Because it's pretty easy to interpret and it's pretty easy the math behind of the deterministic model, right? The generalized least square is a little bit more complex. And if you can use something simple, why you want to overcomplicate your life, right? Well, that's everything about the simple and multiple regression linear models and about the covering the assumptions. And the next step is to interpolate the first and the second order trend surface with the grid that we created at the previous lesson. Now I am going to paste the code that we created the other day for the grid. And I'm going to run all this code just together because we know everything about this code. And I don't want to talk because we already talked about how it works at the previous lesson. Then in this case, what we are going to create is a regular grid for the second order trend surface. Then I'm going to run everything together. Then that's it. And now I'm going to paste here the code related to the interpolation of the predicted values inside of this grid. Then paste here. And let's go to talk about this section of the code. Then we are going to do the second order trend surface and we are going to interpolate the data inside the grid. We are going to use this function that computes the best fit and the 95% of the prediction interval. That is going to be 2.5% at the lowest and 2.5% at the upper. Then we need the grid as a data frame. That is really important. That's the reason because here at the top, we make our grid to be as a data frame, okay? And that's the grid that we are using. Is the same as this one over here. Then we are using the model 3 that is related with the second order trend surface. With the interval prediction, we are saying that what we want is the best fit and the 95% of the prediction interval. And this one is the interval that we decided to put, that is the 95%. Then we can run this code. Then we want to see the class of this object. As you can see, it's a matrix array. Then we want to see the summary. Here we have some statistics. As you can see, now we have 3 different parameters: the best fit, the lowest, and the upper. That's related with the 2.5% and the 2.5%, okay? And that's the predicted values at the model, okay? Then we can see that information in a table. As you can see, it takes a little bit time to load because it has a lot of information, right? Now we have, for each of these pixels, we have one value, right? And remember that these pixels are 500 by 500 meters. And that's because we have a very long table with a lot of data. And this data is for the best fit, for the lower and for the upper. Now what we want is to convert the grid. Remember that we have this grid, and this grid is a data frame. If we go here to the table, it's a data frame. Now we want to convert this data frame to a spatial point data frame, okay? And we are using this code over here. Now you're going to see that this object is going to change from a data frame to a spatial point data frame. Then we can run this code. As you can see, now it changed. Now the next step is to create the grid with the predicted values as a spatial point data frame, okay? And to do that one, we are going to use this code. Then it means that we are going to take these three values and we are going to put these three values from this object inside the grid, inside this grid, okay? And how we are going to do that one? Using this code over here. Then we are saying that the coordinates, it comes from this grid over here, and the data that we have in this object, that is the predicted, let me show you this object, the predicted for the second order trend surface. Let me see, what is that one? Predicted here is this object over here. We want this one as a data frame inside the grid, okay? Then we can run this code. Now we want to convert the grid a spatial pixel data frame. The object are points in a regular grid. Then we can run this code. And then the next one, improving the computational efficiency by using the full grid. With this function, what we are going to have is a computational efficiency, okay, for the computer. Then run this script. Then what we are going to do is assign the reference coordinate systems to the new grid. Okay, now we have this grid, okay? And we want this grid to have these reference coordinate systems. Then first we say that the coordinate reference systems is this one, and then assign the coordinate reference systems to this grid, okay? Then run and run. Now we can check the characteristics and the statistics of the new grid. Then run this code. And this is the characteristics. We have the coordinates, the maximum, the minimum. We have the reference coordinate systems for the grid. Remember that this one is the predicted grid. Now already we have this grid, and inside this grid we have the fitted values that are the predicted values, plus the lower that is associated with the 2.5% of the prediction, and the upper that is also associated with the 2.5% of the prediction, okay? Then we have here the characteristics of the cells, and here we have the parameters that we have inside the grid. Next step is to create a graph where we plot just the fitted values. Then we are going to say that this object that is going to be called with this name, and we are going to plot the graph using this function. And what we want inside, we want to use this grid, and the value that we want to represent on the graph is the fit, is this value over here, the fit. The fit is the fitted value, is the predicted values. Then we can run this one and print the graph. We have to leave the software to create the graph. It takes a little bit of time because there is a lot of data. And here we have the result. For the interpolation, for the second order trend surface, according to the ordinary least squares. And this one is a surface of a second order. Next step is to convert the new grid a data frame. Remember that now we are working with this grid. Why we want to convert the new grid a data frame? In order to manipulate the variables inside the grid. Then we are going to run this one, and we are going to call the new grid with this name. This new grid is going to be a data frame of this grid, okay? Then, as you can see, if we check the predict grid over here, predict grid is a large spatial grid data frame, okay? But now we are going to create a new grid that is going to be again a data frame, okay? And it's going to be saved with this name over here. Is number 2. Now we convert this large spatial grid data frame to a data frame, and we save with this name. Now we can see the table. And what we want to do that one, because we want to manipulate this data over here, right? We like to have the X and Y in this part of the table, and maybe we want to remove this one and just use only this column. Then let's go to see how we can do that one. Then we are going to load the library, this one, to remove from the data set, that is this data set, the columns associated with the lower and the upper predictions with the 2.5%, right? But I'm not sure if I have this library. Let me check. Yes, the library is already loaded. Then with the next script, we are going to use a new data frame that we are going to call with this name. But in this new data frame, we are going to remove this one and this one. From what data frame? From this data frame. Remember that this data frame was this one. Then we are going to create another data frame, but we are going to take this one and this one out, and we are going to leave the fit, the X, and the Y. That is the values that I want to have at the data frame. Then I'm going to run this one. And then we can see the new data frame. That is going to be the predicted grid number 3. Okay, as you can see, we remove it. And now we have these 3 values, these 3 parameters, okay? X coordinate, Y coordinate, and the predicted values. Next step is to fix the order of the columns. Okay, we want to have the first column to be the number 2. The number 2 has to be the first column. The number 3 has to be the second column, and the fit values has to be the third column. And that's what we are saying here. Then we want the first column to be the number 2, the second column the number 3, and the third column the number 1. Okay, we have number 1, number 2, and number 3. Then we can run that one. And we save that one with a different name. I'm changing the name all the time for the grid, but you can still using the same and make the modifications. But I would like to keep the original data frames, because if I want to change something more, or I don't like the change, or I want to do another modification, I'm always have all the grids I did the modifications, right? Always the data frame that I make the modifications. Then now we can see the results of the table. And as you can see, now we have the first column X, the second column Y, and the third column the fitted values that are the predicted values. And as you can see, this table is very long because we have, again, all the values for each of the pixels at the grid. Then the next step is to create a raster with the new data set, that is the number 4, to be exported to QGIS, right? We want to have a raster, and this raster is going to be georeference, and then we want to open this raster in QGIS. Then to do that one, we are going to use this one. I don't think so I have the raster library, but let me double check. Okay, the package is not fine. Then we have to install that package. Then we are going to install the package. And it's going to be this one, but we want to put here this one and put raster inside. And now we can run this one. I don't know how long it's going to take to install this package. If it's very long, I'm going to pass the video faster. It's already installed, then now we can run the library. Then I'm going to create an object that is going to be this one, second order trend surface, and it's going to be equal to this function. Then with this function, we are going to create the raster file. I want to convert this data frame, the last one, the number 4 is this one, as a raster. Then we can run, and also we can plot this one. But as you can see, you cannot see really well. Then you can clean all the plots here, yes, and we can run this one again to see well. And that's the final result. And that's the raster that we are going to export to QGIS to work with this trend surface in QGIS. Now that we have the raster already created, we are going to do the exportation. Export the second order trend surface according to the linear regression ordinary least squares. And we are going to use this function over here. But first, let me put a pound over here because I don't want to run this line again. I'm going to save, and also I am going to open QGIS. And let's go to talk about this line. Here we are saying that we want to export this object. That is the same as we created over here. We want to add this name to this object, second order, cell 500 meters. We don't want to have any pixel with there is no values, right? We want to avoid that situation. And we want the overwrite to be true. Then where is going to be saved this object is going to be saved at the folder that we created at the beginning, inside this folder. Then we can go down and export the object. Oh no, sorry, not this one. That's a different thing. Is this one. And also with this function, we can see the files inside that folder. And as you can see, we have here the one we want. Now let me open the lesson number 2 that we have the WorldCamp aquifer data set. Let me take this one out. Let me put the piezometers. Let me change the color of the piezometers for a red one maybe. Apply. Okay, now we can see well. We can change the hybrid satellite imagery for the regular satellite imagery. And now let me show you that folder. Is this folder. Inside this folder, now we have here the raster file that is georeference. And now we are going to open this file in QGIS. Then go here, select raster, go to the folder, this one, double click, open, add, close. Is this one. As you can see, there is no coordinate reference systems. Then we have to add the coordinate reference systems. Is this one. Okay. And now we can edit this layer, properties. Here, select this one, equal interval. I would like to see discrete and with 10 intervals, or 10 different classes. Then apply, and that's the result. Now we can put the piezometers on the top. Now we have the second order train surface associated with this data according to the ordinary least squares. The next thing we want to do is to create, as you can see over here, creating table with the residuals to perform the ordinary kriging in QGIS. Then what we are going to create is a new table that is going to be saved with this name, that is going to be the same as the table A2. I put A2 here because, as you can see, A is no longer a data frame, okay, because we modified that table. And then I'm using the backup because the backup is still a data frame, okay. Then we can run this line. We can see what we have in this table. Copy, and we can put here view table. Then paste this table inside. We can see this table, that this table is the same as the original one, right? We have the ID, we have the X coordinate, we have the Y coordinate, and we have the groundwater elevation. Then we want to have this table, but with the residual values and also the predicted values. In that way, we can use this data frame in QGIS to perform the ordinary kriging in QGIS with this table. Because we are going to do the ordinary kriging, right, with the residuals. And then we are going to plus the trend surface, this trend surface, plus the ordinary kriging interpolation of the residuals. And when we plus these two raster layers, we are going to have the final result. We are going now to add the residual values to the new table. Remember that we already extracted the residuals previously when we was doing the histogram, and we use this line, okay, at the top. Then we have this object that has already the residual values, and residuals has to be over here, this one, okay. We have an object already with the residuals. Then we are saying here that in this table, that is the one that we created now, this one, we want to add a new field that is going to be called residuals, and this field is going to be equal to this object, that is the residual values. Then we can run this one, and that's it. Now what we want to add is the predicted values to the same table, but in this case we have to extract the predicted values. Then we are saying that this object that is going to be called predicted 3 is going to be equal to the predicted values from the model 3, that is the model associated with the second order trend surface. Then we run this script. Now we have also the predicted values, and we want to add in this table a new field that is going to be predicted, and this field is going to contain the predicted values associated with the second order trend surface. Then we can run this one. And at the end, also we want to add a quality control. This quality control is the summation of the residuals and the predicted. When we plus these two values, what we are going to have is the groundwater elevation, right? Then we are going to add a new field in this table that is going to be quality control, and it's going to be the summation of these two values. Then run. And now we can see the final table, and it's this table. We have X, Y, we have the groundwater elevation, we have the residuals, and we have the predicted. These residuals and predicted values are associated with the ordinary least squares, okay, for the second order trend surface, and we add the quality control. That it means that this one plus this one has to be equal to this one, and this one has to be the same value as the groundwater elevation. Now it's time to export this table. Then to export this table, we are going to use this code, but we want to specify when we want to save the spreadsheet of this table, right? Then I'm going to create a new folder here, for example, this one, and I'm going to put here a data set. And in this folder, I'm going to open and I'm going to copy this link, copy the link. Then I'm going to paste this link over here. Sorry, from here to here. And also I'm keeping this one because I want to save with this name the file, okay? Then I paste here. But I have to change the direction of the dash bars. And it's pretty long. I don't know why that one is duplicate. Okay, let me see. Oh yeah, it's duplicate here. Okay, that's good. Then we can run this script now. Run. And we can go to the folder. This folder, data set. And now we have the spreadsheet for the residuals and the predicted values. Then as the format of this file is a CSV, we can open this one in QGIS. Okay, and it's this one. We have the X coordinate, the Y coordinate, the groundwater elevation, the residuals, the predictives, and the quality control. And we have for the 85 observations, that is the total number of the piezometers. Then at the end, what we have is the deterministic model, that is this one, the second order trend surface, and also we have the residual values. Then we completed already this part of the regression kriging because we have the trend surface, that is a deterministic model based on ordinary least squares, but we didn't solve this section. That is going to be the ordinary kriging. How we can solve this section? Using the residual values here. Then in order to complete the regression kriging, we have to do the ordinary kriging with the residuals. But I'm not going to do this section, the regression kriging, the final result, you know, because I don't know which of these models I'm going to use to do the full regression kriging. Today we completed the ordinary least squares, but we have to do the generalized least squares, we have to do the generalized additive model, and also the thin plate spline interpolation. Then at the end we can take one of these ones and apply the ordinary kriging to the residuals. But one more thing I would like to do in this lesson, that is going to do create the first order trend surface. Then what I'm going to do at the moment is remove all these sections over here, remove all these sections over here. I'm going to restart also the we don't want to save the R. Let me close. Open again. Then what I'm going to do is remove all the coding that we created for the second order trend surface from here. And then I'm going to paste for the first order trend surface, okay? I did already all the coding. As you can see, we are going to create again the grid. That one is going to be the same as we did for the second order train surface, but for the interpolation, in this case, we are going to do the interpolation for the first order train surface. Then we are going to use the model 2. Remember that previously was using the model 3, that it was related with the second order train surface, but now the model 2 is related with the first order train surface. And then I did all the modifications here to be adapted for the first order train surface. Then what I'm going to do now is to run all the code. Then I'm going to close this one here. And I'm going to select here, select all. And I'm going to run all the code again. The process is already complete. Now if we go to the folder for the data set that we created, this one, double click. Now we have also the residuals and the predicted values for the first order train surface. I'm going to open this one. Is these values? As you can see now, these values are different from the second order train surface. As you can see, for example, for the first value, the residual here is 24.7 for the first order train surface, but for the second order train surface it was minus 13.78. okay, now we have different values for the residuals and for the predicted values, but for the quality control has to be the same values. Okay, then also we can go to the folder here, and now what we have is the second order train surface and also the first order train surface that now we are going to load on QGIS. Then go here and we are going to select the first order train surface. That is going to be this one. Open, add, we can close this one. We can add the reference coordinate systems, that is this one. Okay, and now we can edit this layer properties. Select here single band pseudo color. Then we want equal intervals for 10 classes. And we want also here to be discrete. Apply and OK. We can move the data set to the top. And also we can move this one over here. And now we have the first order train surface and also the second order train surface according to the ordinary least squares. Then we can use any of these two train surface to work with the regression kriging. Well, that's it for today. Thank you very much for watching this video and see you on the next lesson.